I didn't erase this. So lesson 3.5 is on compounding interest. And interest kind of leads into what we did before on 3.3, where we're given this formula, like f of t or f of x is equal to a, so initial value, times 1 plus r to the t. Where we have a rate, we have initial value. Actually, I'm not going to label it too much because we're going to scrap this and like do another one. So initial value, rate, and time. Where interest builds up and up, exponential growth is kind of the strongest thing we've seen so far. It's stronger than linear because linear is just a straight line. Linear is like that. Quadratic is like this, but exponential, we're increasing by in terms of x, and that is so much more steeper and stronger than quadratic, or even like cubic, because there comes a point where if a bigger exponent, the much stronger the slope. But this formula doesn't work for all scenarios. The main scenario, compounding interest, one thing we think about with this is money. With money, it's not changing at a constant, like at a continuous rate like this. It's not quite continuous. Money, and once you get a bank, you'll see, or if you do have a savings account, you'll see that I get notifications every couple of months, and it tells me, oh, like my savings account yielded some profit, because they only do the interest once in a while. So let's take something real quick. Let's say we have, I'll actually type this. How do I increase font size? Here. 28. You have $1,000 to deposit in a bank account. So we have bank 1. It offers you 12% per year interest rate. There's a lot of keywords here, which we'll talk about. And this thing is a per year interest rate. And this is paid out at the end of each year. So we have bank 1. Let's look at bank 1. So bank 1, let's say A of 1 equals, let's see, my initial value is $1,000 and my rate is 12%, so 1 plus 0.12, and the time, just 1 year, because we're talking in terms of years. It's 12% per year and it's paid at the end of each year. So at the very end, I get paid and I see how much money I have in my bank. So this, a bank 1 gives me 1,000 times 1.12 to the first powers is that. So you get $1,120. I made $120 in that year off of interest. And that seems great. What else could there be? What there could be is, actually, let me just copy this, paste it, so I don't need to change the font size. Oh no, how that works. So now we have bank 2. It also offers a 12% interest rate, but instead of paying at the end of the year, this bank pays equal parts of the interest at the end of each month. So equal parts of the interest at the end of each month. That is a bit confusing, but we'll see how much interest is there. We see 12% interest rate per year. 12% per year interest rate. 12% per year interest rate. Let me just stretch this out then. 12% per year interest rate. So if it pays interest equal parts, if I have 12% per year, it's being split across 12 months. So it's 1% each month. Each month. So that's my new rate. My bank 2 is equal to $1,000 plus 1 plus my rate is 0.01. But how many times am I applying this interest? I'm not applying it once. I'm going to apply it 12 times at every single month. I'm applying this 1% interest rate 12 times. A2 equals 1,000 times 1.01 to the 12th power. And applying this, let me look at my calculator. 1.01 to the 12th power to, where was it? I can't see it. What the heck? Let me pause. Okay, so I found it. 1.01 to the 12th power is 1.1268. That times 1,000 gives me bank 2 1126.83 cents. And comparing this to bank 1, we see bank 2 yielded more money than bank 1, even though they both gave a 12% per year interest rate. Now this is the first thing about compounding interest. More intervals across the year, across the same time frame, if I split into different parts and apply interest more times in that time frame, I then yield more money if I'm given the same interest rate at a same rate. So this, but then this formula that we did here, splitting into 1% each month, saying that's 12 because it happens 12 times in 1 year. I want to generalize that into a better formula. So we take what we had over here and we see a, my function a of t. My result, how much money I have as a function of time. That's equal to my principal value, so p, my initial value, principal amount, so initial, times 1 plus, so I'm starting with 100%, my rate, but my rate is being divided by the number of times I split it, the number of time periods I have. And that number of time periods also applies to my time. It's not like I'm having more time. It's like there's more times I am applying this interval. So we call this R is my interest rate, often for a year, because money often talks about year. And my N is my number of compounding periods. It is also per year, most often. So I have my formula, kind of messy, but we see A of t equals P times 1 plus R over N to the NT power. So let's apply this. Let's see how this works. So, oh man, suppose $600 is invested in a bank that pays 6% annual interest. Reading over this once again, suppose 600, that seems like my B. We're investing $600. So I have my formula. I'm going to rewrite my entire thing. I see this, probably my P. I'm investing that much. Oh, that's terrible P. And it pays 6% annual interest. That annual is key right here. 6% annual, so that I have a happy R. 60% is my R. What am I missing? My N, my T, and maybe A. Like always, for an equation like this, you could only have one missing variable to solve for. You cannot have two missing variables in one equation. Then we cannot solve it. So let's give it this little piece right here. How much is the account worth when it is closed after 5 years if the interest is compounded yearly? I kind of bolded it, but it's already kind of bold. So it's being compounded yearly. So how many times per year are we compounding interest? Only once. So N is 1. We plug it in. So A of 5 years is equal to, because 5 is T, $600 times 1 plus 0.06 over 1, 1 times 5. And this is just a calculator problem. So we practice a lot with calculators, make sure we get it. All right. So we have this, we solve it out. My 600 to 1.06 to the 5th power. Doing some nice little mental math. Definitely not using my calculator. And I get a value of $802.94. I got quite a bit of money. My $600 became $800 after 5 years. And 60% is a lot higher than most. It's really hard to get 6% interest, but it is manageable. And I got $802. Some free money. Now, let's compare it. And we'll do some more examples. I say, what if it's now quarterly? It's compounded quarterly. So how many times per year is quarterly? That means now N equals 4. So A to the 5th, not A to the 5th, A of 5 is 600. 1 plus 0.06 over 4. It's decreasing, rate's decreasing, but it's increasing over here, 4 times 5. And once again, let me do some mental math. So I have 600 times 1 plus 0.06 divided by 4 to the 20th power. And I now get a grand total of $808.11. A whole, not even a whole $6, less than $6 more if it's done quarterly. Let's say now, what if it's done monthly? Monthly is now N equals 12. This seems kind of redundant. Why are we doing it over and over again? Because I want to practice using this formula, but also practice reading comprehension. With word problems, you have to see a lot of checklists. I have $600. It's annual interest. That annual might trip you up. But now you want to see, oh, it's being compounded monthly to my annual interest. So my annual is my baseline, and splitting my annual into months is 12 months. Let's see, it could be like 6% hourly interest, and my interest is being compounded minutely. So now my hour is my baseline. My minutes, I have 60 minutes in an hour. So then becomes N is 60. That will rarely be the case. I don't know if we have problems like that because that's not a real life scenario, and we try to keep it attached to kind of realish scenarios. But we'll just solve this out. A of 5 equals 600 times 1 plus 0.06 divided by 12. 12 times 5. Once again, doing some mental math gives me a grand total of $809.31. Let's observe these numbers real quick. So I went yearly, I got $803. Then increasing it to 4 jumped my money $5 and some change to $808. And a monthly, so for 4 to 12. Still a big increase. So 1 to 4 increased by 3 or times 4. 4 to 12 increased by 8 or times 3. So still relatively comparable increase. But I got $1.20. You can assume that, let's say 36, doing it 3 times a month, might break $810. But going further and further, you can assume that it's kind of plateauing out. It's getting closer and closer to a certain point. And we now want to find this point. So this is now continuous growth. Why do we do this, and why do we leave it until after testing exponents to talk about compounding interest? Because compounding interest ties directly into logarithms because we have a special value. So let's say we have $1. P equals $1. And my interest, my rate is 100%. So A equals $1, 1 plus 1 over n. And let's say my t is just 1 year. So nt, or just n times t. And times 1, I just get rid of that. So my final result, let's say, gives me this one disappears, that one disappears. So I have 1 plus 1 over n to the n power. This will tell me how much money I have if I have $1 deposited at an interest rate of $100. Why are we doing this? Because we want to see, as we increase n, what does this rate become? How much are we doing with this rate? So I want to get n to be as big as possible. So let's say annual. Annually compounded. So n equals 1. 1 plus 1 over 1 to the, not n, to the 1 gives you 1 plus 1 to the 1 equals 2. After 1 year, if I have 100% interest rate and $1, I have $2, which makes sense. Now monthly. N equals 12. 1 plus 1 over 12 to the 12. We know that it will have to be bigger. How much bigger, you say? We have 1 plus 1 divided by 12 to the 12th power equals 2.61. Much bigger, but there's still more to go. Let's say daily, not a leap year. N equals 365. 1 plus 1 over 365, 365. I messed up. No, I didn't mess up. I'm just doing it in my head. This gives me 2.71 or 72. Just 71. Increase by 10 cents. So 60 cents, 10 cents. Let's just say just as much as possible. 100,000. I want to do it 100,000 times. This gives me a grand total of, if my calculator, no, not my calculator. If this lets me do it. $2.7183. And why do we do this? We're trying to see, as we do it more and more, let's say now, I don't want to do it annually. I don't want to compound my interest monthly, not even daily, or even to the 100,000s. I want to do it every single millisecond, every single fraction of a millisecond. I want to do it over and over so it's never not increasing. And this growth may not apply to money, because if they did this, then the bank is giving so much more money out than if they did annually. But this often happens with stuff that can't be done by set time periods that people set. Because humans can be like, oh, we could do it monthly. But not everything is in control of us. One thing that's not is population of both people and bacteria, of like livestock, of people groups, of animals. Population, we can't really control it, especially with bacteria. Also, it could be used for is, let's say, like half-life, radiation. Back in our scenario, think back to what you did for your scenario in your project. A lot of that stuff is continuous. And we did a kind of basic version of a times 1 plus r to the t. But this is a lot more useful. We now want it to be a continuous growth. So this gives us E. E, we have a constant E as 2.7183 ... It's similar to pi where it's infinite growth. And this is used for continuous growth. Continuous growth / decay. It's called Euler's number, but I'll call it E. And continuously compounded interest. Compounded interest. This applies when the interest, the change, is being applied constantly to the principal. So my initial value. And this is given to us by A equals P E R T. Really kind of weird, but we have P times E to the RT power. A of T equals P E to RT. Where A is the account total still. P is my principal. So this is my account. This is my principal, my initial. E is my constant, and R is my rate. And there's no end now because it's applying continuously. So let's now use the same problem that we had before up here. 6% annual interest, but let's say it's now continuous interest. It's at a continuous rate of 6%. So I have $600 being applied to E at a rate of 6% of 5 years. This is A of 5. The E button on your calculator should be on the scientific one. I'm not sure which one you have at home, but it'll be at the top left corner. And this gives us a value of $809.92. So if we see it is greater than this. If I continue this monthly to be daily to be 100,000, it'll get really, really close. And we see 100,000 did get 2.7183. E is roughly 2.7183. 100,000 would probably give us this because money kind of stops at two decimal places. But with a large problem, those numbers become more and more important. And the difference between monthly and daily and annually becomes much more greater. So this is, I'll say, part 1 of compounding interest. There's not many questions we did. I'll probably add part 4 later. So part 3 next will be on more log properties, and part 4 will be touching back on this, doing some more problems with this, more advanced problems. But yeah, if you have any questions, feel free to email, feel free to show up in class and let me know. Bye-bye.